What is going on, everybody? It's Mr. Gus, and I'm back in the physics conference room. Today, we're talking about waves. It's our new unit. We're going to be discussing waves, mechanical waves, sound waves. We've already kind of discussed electromagnetic waves, but different kinds of waves is what the topic of this unit is. So, when I think about the word wave, a number of different kinds of waves come to my mind. A wave of emotion comes to mind. An ocean wave comes to mind. A hand wave, like at the University of Iowa football games. A wave around the stadium. All of those kind of waves come to mind. And they all are called waves. We're talking about kind of the noun wave, and we have a physics definition for this wave. The definition of a wave in physics is specifically a disturbance that transfers energy through a medium or space, but it does not transfer matter itself. What that means is that matter, objects in space, or maybe not, will move, and that will transfer energy through that medium or space, but it won't actually transfer any material, right? It just transfers energy through a medium if we're talking about a mechanical wave. Obviously, electromagnetic waves aren't going to transfer matter at all because they travel through empty space all the time. That's how we get sunlight to the planet Earth. Okay? This is our definition. Now, if we think about this definition in kind of a silly way, we can think about, all right, think about an ocean wave. Like, does an ocean wave oscillate? Do the water particles move up and down, forward and backward, and transfer waves crashing onto the beach without actually moving all of the water from the middle of the ocean to the shoreline? And yeah, absolutely. Like, every time water crashes onto the beach, it crashes and pulls back, and it crashes and pulls back. So we're seeing this disturbance of water, but we're not actually seeing all of the water from the middle of the ocean washing up on shore. The reason the water moves is because of currents and differences in pressure and salinity and things like that. The hand wave, if I'm thinking about a stadium wave. If I think about a stadium wave, that's when people stand up and down and we see the wave propagate around the stadium. Do people move? Like, yeah, they move up and down, but that wave that we see goes around the stadium. Are the people physically moving around the stadium? They are not. They are disturbing themselves by standing up and down, and we see the propagation of that energy around the stadium. Silly, if I wave my hand, am I propagating my hand through space? I am not. But I am waving, moving my hand, disturbing my hand back and forth, and spreading joy out from my hand, the energy of joy, if you will, out from my wave. Now, that's silly. But for our unit, we will be discussing different types of waves. And the first wave we'll talk about is like a mechanical wave on a string or on a slinky or a spring that we'll see oscillate the page. Okay? But that'll come later. For now, we have to just do the basics. And the basics are we have two primary waves that we'll discuss this unit. One, you are pretty familiar with because it's the same shape as an electromagnetic wave you've seen in chemistry. I know you saw it again in physics 1, but we're going to see it again here in physics 2. And that wave is the common wave. It's the sinusoidal wave. It is the transverse wave. Transverse waves look something like this. These are called transverse waves. And transverse waves are defined as waves where the disturbance is perpendicular to the transfer of energy. Now, what do I mean by that? What I mean is, you see, if this is a spring or a slinky and it's fixed here and it's fixed here, and I pluck that string and it makes this wave, the wave itself, the string or the medium, the material is disturbed up and down, but that wave, the energy transfers along that string. So that disturbance and energy transfer are perpendicular to each other. Well, we call this a transverse wave. And there are a few things we can label about this, kind of the anatomy of that wave. We would call this distance the height from the equilibrium position to a peak, or from the height from the equilibrium position to the lowest point. We call this the amplitude. Amplitude. And now an amplitude is in direct relationship with how much energy is being transferred, right? If you pluck a string really hard and give a really big amplitude, we're going to see a lot of energy transferred. And if you want to be really quiet and you pluck the string very gently, small amplitude, there's going to be a lot less energy. That's the point of this whole thing, right? Amplitude is directly related to the amount of energy transferred, okay? So more energy, you're going to get more amplitude through there, okay? That's the first thing. The next thing we have is we can measure a wavelength, and a wavelength is simply the measurement of how long a single wave is. And so the way we define a single wave is we look at two consecutive points, right? So we have basically, for our case, we have a beginning point, and then we go up, we go down, we go back to that beginning point. That's one way to measure wavelength. Some people like to say it is measured from a peak of one wave to the peak of the next wave. That's equally correct because those are two consecutive points of a wave. We can also measure it that way. I like to show one whole wave. So this point here to this point here, that distance, this whole distance, is known as our wavelength. And it's usually measured in some type of meters, right? When we're talking about mechanical or string waves, we might measure wavelength in meters or centimeters. If we're talking about something like radio waves, you might be talking about something like the size of kilometers. Sometimes it's very, very large, massive radio waves. And when you're talking about things like, I don't know, electromagnetic light waves, you might be talking on the scale of like nanometers, like the very tiny measurements, but always in meters, okay? So I've got an amplitude, I've got a wavelength. Now, the wavelength and amplitude are measurements generally of distance. We also have two more measurements when it comes to waves that aren't necessarily easily seen on a sketch of that wave. And they are the period of a wave and the frequency of a wave. Period is the time for one wave to pass through a point. And frequency is the number of waves passing through a point in 1 second. Period is measured in seconds, and frequency is measured in hertz. Now, if you're thinking to yourself, those sound like pretty similar definitions, it's because they are. It's because they're incredibly similar. The period basically says, if I'm going to track how long it takes for this wave, this whole wave, to pass through this single point, that time it takes to pass through that point is the period. But the inverse of that would say, okay, well, how many waves pass through that point in a single second? Well, that's frequency. So they're very similar. In fact, mathematically, we would call them inverses, right? Mathematically, we say period, which is capital T, is equal to 1 over the frequency. That's an equation we have written on our equation sheet. So if you know the period of a wave, the inverse of that's the frequency. If you know the frequency of a wave, the inverse of that is the period, right? Those are inverses of each other with very similar definitions, both related to time components. So we've got distance components, we have time components of waves. These are the basics of the transverse wave. Again, defined as a perpendicular disturbance to the transfer of energy. Well, if that's true, we have the perpendicular wave. We may also have a different wave known as the longitudinal wave. The longitudinal wave is the wave defined as we have a disturbance that is parallel to direction of the energy transfer, I'll call it E transfer. Okay? Now, when I'm thinking about this is a little bit harder to draw, to sketch, right? This one's a little bit trickier for me to show you, but I'll try, okay? So a longitudinal wave, a parallel disruption to the direction of energy flow. Watch this. Like, a lot of people sometimes will draw when I think about a longitudinal wave, I think mostly about sound waves. Sound waves are great examples of longitudinal waves. So if I'm going to draw a cartoon of someone yelling, I might draw someone yelling like this, like yelling, projecting that wave outward from their mouth. Let's go ahead and show how that might look with a parallel disturbance, okay? So if they're going to yell out from their mouth, I'm going to show vertical lines of that disturbance in the air or in the medium they're yelling through. So let's go ahead and say, like, I'm going to have some waves that are further and further apart, and then I'm going to have some waves that get, we're going to make these two be the same size, closer and closer together, and then further and further apart, and then closer and closer together, and then further and further apart. And so we can see here, I'm not sure I'm great at drawing this, but what you see is that there's a area of low pressure and then high pressure, and then low pressure and then high pressure. So we're seeing this disturbance that is parallel to the direction of the sound being transferred or the energy being transferred. Think about traffic, cars in traffic, right? If you're at a stoplight in traffic or you're sitting on the highway in a bumper-to-bumper traffic, your cars are all stacked up. And as the first car gets a chance to drive off, it drives off, and the next car drives off, you drive off. And then the next time you hit a roadblock, you slow back down. And we see this like compression and expansion of the cars in traffic. That is exactly what we're trying to model here with the sound wave. There's an expansion of the air in the room, and then a compression, an expansion and compression. And it's that expansion and compression of the air particles in the room that when they hit your eardrum or your tympanic membrane, you hear or perceive sounds in the room. This is the longitudinal wave. Again, tricky to model, but this is the best I can do at modeling it. Let's look at the geometry of it, okay? If I'm looking at the geometry of it, I would say, okay, what's the amplitude? Well, the amplitude is just how loud something is for a sound wave. We also said it's how disturbed we are from equilibrium. So the disturbance would be basically how close are these waves, right? Or how close are those particles? How disturbed are they, right? If they're really stacked up on top of each other, creating this giant high pressure wave, that would be a very large amplitude, okay? So amplitude is not how tall a peak is anymore. It's how compressed the particles or how expanded the particles are. That's the synonym to the transverse wave. Now, the wavelength, well, we said the wavelength was always going to be 2 consecutive points. So I would look and say, hey, how long is it distance-wise between 2 areas of loud noise or 2 areas of soft noise, 2 areas of high pressure or low pressure? So I would call this my wavelength, and again, it's measured in meters of some kind, some degree of meters, right? The other 2 would be period and frequency. Well, how would I measure that? Those are actually the exact same, right? Period or frequency would be, hey, if this is the point on my, the point I'm measuring from, how many waves pass through that point in a second? Well, that's the frequency. Or how long does it take for one wavelength to pass through that point? That's the period. And again, they're inverses of each other, okay? To recap, we have waves. Waves are disturbances in a medium that transfer energy but do not transfer matter themselves. That's the definition of a wave. We have 2 primary kinds of waves that we are looking at. We have the transverse wave, perpendicular disturbance to the energy transfer, and we have the longitudinal wave. The longitudinal wave is the parallel disturbance to energy transfer. Those are the key takeaways, and then obviously we have the geometry of these waves. Those are the key takeaways from this video and from the introduction to waves, okay? If you got questions, you drop in the comments, you send me an email, or as always, ask me in class. Till next time, see ya.